feel like as part of this meeting, it's a real honor to speak to everyone. I feel like I'm speaking on behalf of International Women in STEM Day and allies. So it's lovely to be here. And I am sporting some of my swag from one of my favorite women with an international background, as we all know. And really, it's wonderful to celebrate females in science and in other branches of the world and society where we're all making an impact and making a difference. As I come to you today here from Pennsylvania, the weather is lovely and it corresponds with what you can feel as a change in the country, a change in the field. And I really think that there are brighter days ahead of us. I know that everything is looking pretty sad right now in terms of us not being able to fully be engaged and at work as we would be in other times. But there are bright days ahead and bright moments to come as we see things changing in the world, in the US and in other societies. We're starting to see people become vaccinated. We're starting to see people become healthy, and that we're hopefully turning a corner in terms of all gathering together again and being able to come together in the lab environment, in the research environment, even through computing means, and actually be in person for upcoming conferences and meetings. And I'd like to say, as the president-elect of the Microscopy Society of America, we're really hoping that we'll be able to meet in person this year in August. If things are good in terms of what we're hoping to see, we'd like to have an in-person meeting. There's no guarantee. We may end up having a virtual meeting. We'll know in just a few weeks we're going to make this decision. So please stay tuned, and everyone please attend if you can. It's wonderful to see young scientists present posters as well as give invited talks. And I'd like to give a shout out to the MSA Student Council, who's done a wonderful job of engaging future scientists and leaders of tomorrow, that hopefully you'll have my job one day and just take over MSA and bring us into grand new directions. So as we look at bright times ahead of us, wouldn't it be great if we could all gather in August for M&M, where we can gather in the future this fall to have in-person classes, to have in-person research, and even if we're able to meet right now in small teams and in small groups to actually accomplish research goals, it's going to make a big difference in the world. And so it's a real pleasure today, also rising to the occasion. It's wonderful to celebrate everyone. I do want to give a shout out that Penn State is recruiting tenure track faculty in the College of Engineering, and we're hoping to do this through means of equity and diversity. I'm on the committee who's helping formulate this. There's no limit to the number of people we're recruiting. We're just interested in recruiting talented people. There's also no deadlines. It's going to be a rolling basis, and I have that ad ready to go, and I can share that with the organizers to distribute. So our goal is just to everyone come together and to build a great future based on diversity and inclusion. And the more females we can have be a part of that, the better. We're actually should be asking the question, diversity first. How can we all come together? Because diversity in mindset, diversity in experiments, diversity in collaborations, diversity in PIs really makes the grand collective here. And we're hoping to move forward with that, both at our university, I'm sure, at Northwestern. This is the second time I've been honored with speaking with you in your program. And each time it just gets better and better. So without further ado, I'll turn it over to the next speaker. And I look forward to hearing the wonderful talks today. If anyone is interested in information about Penn State or MSA, please reach out. And I look forward to future discussions and connecting with everyone in the future as we move forward into in-person learning and meeting environments. Thank you.
And so I have some prepared remarks, if you bear with me for a minute or two. Obviously, I'm very delighted to welcome all of you to this rather special event today to celebrate the International Women's Day. I'm very thrilled to learn that hundreds of attendees are being represented across dozens of countries, which is remarkable. And given that likely many young students and young colleagues are attending this event, maybe I should paraphrase this specific event in the microscopy contest, given that we are commemorating women in microscopy as a part of this event. So the best way to say it is like, imagine looking at only half of your TM grid or half of your scan sample and SEM and TM. So in a way, for many generations, even my own alma mater at Lehigh didn't become co-ed until early 70s. For generations, the science and technology and microscopy community pretty much missed start of half of our society. But looking at today's program, you can tell that we have come certainly a long way, but we still have a long way to go in terms of many other aspects of inclusion. But at least with respect to the event today, I'm just so thrilled and so proud, and to be truly honored to be part of this. And everything is coming together so amazingly, so nicely. So many of us, on a personal note, as you can imagine, we grew up with very strong women and inspiring women, particularly my own mother, who was actually barely finished high school, but she made sure that her children receive education. This is a major equalizer. And I hope education is something we can offer to all of the members of our society as we move forward. And then particularly, even my current cohort of students, as you can see, it's been organized by a number of women in my group. So I'm very excited to celebrate this Women in Microscopy event. This particular event is a part of a NUANCE and a SHINE resource. These are the two centers. The NUANCE Center is something I started some 20 years ago. And now NUANCE is the lead facility as a part of our SHINE resource, which is our NSF Center of Excellence for Facilities and Infrastructure. And the next slide shows our sort of approach, our strategy for both education and inclusion, as well as equity. So if I could have the next slide, I can describe that idea. So what we're trying to do as a part of this event that you see today is we're addressing the various stakeholders that we need to incorporate. And as we move microscopy, nanotechnology, pick up any field moving forward, from K through 12 to university faculty that we are all part of, to also industry, entrepreneur, and of course, public and community. On the left-hand side, you see our outreach and education activity aligned with the stakeholders. And the right-hand side, for those of you who are interested, I'll be happy to share the slides. Diversity and inclusion strategy that you see on the right-hand side. So together, I think we're advancing not just one particular theme, but multiple scientific technological themes as a part of our NUANCE in the SHINE resource. So before I close and introduce the next speaker, I must thank a number of people who organized this. Tirza, Stephanie, the ones I'm familiar with, Katie, Jordan, and many other, our administrative team of NUANCE and SHINE. They work awfully hard, and it reflects on an amazing program that you see here. And I can't wait to hear a lot of you and looking forward to learning many things. With that, I think my next job is to introduce our next speaker. Is that right, Stephanie?
Yes, please.
All right, so let me do that. The pleasure to introduce Ilke Arslan, who's our neighbor at Argonne National Lab. She serves as the director of both the Center for Nanoscale Material, which is the DOE Nanoscale Program, Nanoscience and Engineering Center Program, as well as the newly formed Nanoscience and Technology Division at the Argonne National Lab. So Ilke joined just about a few years ago in 2017, initially as the group leader for electron and X-ray microscopy. And having being a part of Argonne Advisory Committee, I've been very familiar with Ilke for many years. Before Argonne, she worked as a senior scientist at another fantastic national lab, Pacific Northwest National Lab. She also held faculty position in chemical engineering and material science at UC Davis, and where she was actually a very coveted Truman Fellow at Sandia National Lab prior to that. So Ilke has a doctorate in physics from the University of California at Davis, and she's been honored with Presidential Early Career Award for Scientists and Engineers some years ago, as well as the Kavli Fellowship from the National Academy of Science. She's a part of the Strategic Laboratory Leadership Program in 2018 cohort, as well as the Oppenheimer Science and Energy Leadership Program of 2019. And it's a real pleasure, personal pleasure. She has been really going gangbusters at Argonne with especially a field of my great interest, microscopy, setting a fantastic capability. So it's my personal pleasure and a real delight to introduce and listen to Ilke Arslan from Argonne National Lab. Thank you.
Thank you so much, Vinayak. That was a lovely introduction. I really appreciate it. Let me see if I can share sound and share my screen here. All right, can you all see that okay? Because I can't see you anymore Let me see if I
Oh,
can figure out.
great.
It's
Okay.
good.
Great, thank you. So I'm going to be speaking blindly here because I have, I can't see anybody. So I'll just go ahead and put this into presentation mode and proceed.
They're
It
all
is a real
smiling.
I'm sorry, you're all
They're all
smiling?
smiling at you.
Okay, wonderful. It's a real pleasure and an honor for me to be here. Thank you very much for inviting me. As Vinayak mentioned, I have not been back in Illinois for too long, only since 2017, but I started my journey here. So I know that there are a lot of students and postdocs and young people here, and I was asked to sort of talk about both my journey as a female scientist as well as some of the science. So instead of doing science first and then journey second, I just tried to kind of blend those together. So here we go. So it's basically my story interweaved with science and motivations and interests and why I took the directions that I took. And I think that as microscopists, I think you will also perhaps agree that technique development leads to the discovery of new science. And throughout my career, I've really ended up doing that. It certainly wasn't planned, but I've certainly ended up doing different technique developments within the TEM that could lead to the discovery of new science. So I started off my journey here in Chicago, Illinois. I grew up in the city downtown, went to Chicago Public Schools. I went to Lincoln Park High School, for those of you who know where that is. And then I attended the University of Illinois for my bachelor's and master's in physics. And I know we have a speaker or panelist coming up who is at that microscopy center at UIC. I can tell you 21 years ago, Alan Nichols was one of my first microscopy teachers, and he put the fear in me of how to do microscopy right and not break holders and not break microscopes. So his teachings have certainly stayed with me. And then I moved on to Davis, California and Lawrence Berkeley Lab to complete my PhD. So my PhD is from UC Davis, but I did a lot of my, most of my work actually was all at Berkeley Lab. And I will say that this is the first of 4 national labs that I worked at. And it was the National Center for Electron Microscopy at the time. And it's, of course, merged now into the Molecular Foundry once the nanocenters were formed. So I spent most of my career working on STEMs rather than TEMs, and I think most of you know the difference. It's a scanning transmission electron microscope. And this Joel 2010F is the very first microscope that I started and did a lot of my PhD, my initial PhD and undergraduate microscopy on. And then we have aberration correctors that came up right around 2002, like early 2000s, and then monochromation as well. So I did start using all of these things during my PhD time. And then, of course, some of the newer microscopy is ultrafast electron microscopy, new detectors, deflectors, time resolution, lots of cool stuff that we'll be hearing more about later today, not from me, but from my esteemed colleagues here. So in 2002 to 2004, I traveled around, this was during my PhD, to work with the pioneers of aberration correction with Andre Krivenek, with Peter Nellist, Andrew Blaylock in England. I got a bunch of my results for my PhD thesis there at the Daresbury Center there they have a lot of aberration corrected instruments there, which are VGs and now NEONs. And I was looking at dislocations in gallium nitride. So trying to understand these very small dislocations inside of these crystals and understand how that affects their how the electronic properties of these dislocations affect the properties of the materials as LED devices. So gallium nitride is used as an LED material. And when it's put together with aluminum and other types of materials to change the band gap slightly, it can luminesce in red, green, blue. And if we can put those colors together, we can get white LEDs. So this is something that was happening in the early 2000s again. So we wanted to figure out what was the effect of the dislocations, because there was a really, really high density of them, which would have been detrimental in materials such as silicon. Why wasn't it such a problem in gallium nitride? And it turns out that the reason is because they were not electrically active. So I did a bunch of aberration corrected microscopy, monochromated spectroscopy, and I even tried some DFT calculations as part of my PhD thesis and decided I wanted to stick to being an experimentalist to figure out the fine structure and details of what was happening in gallium nitride and at dislocations. And this is kind of a noisy spectrum, but I will point out that we were using a angstrom-sized probe to put on top, directly on top of various parts of the dislocation core. So this is a stacking fault that is connecting two dislocation cores. And we were able to get different spectroscopic signals. So this is the nitrogen K edge, an eel spectrum. And you can see that in the bulk, this first peak here is just a shoulder onto the second peak. And then as you move within this stacking fault from something that looks bulk-like, this 9-atom core, and as you get closer and closer and closer to the 7-atom ring, other end, dislocation core, other end of the stacking fault, you see that the atoms are coming closer together. And so what's happening is that they are separating further apart in the Z direction. And when that happens, that changes the bonding, and it changes, and we can see that change from through the spectrum. But the important thing is that there are no states formed lower in the band gap, which we also looked at with DFT calculations. And so these dislocations are electrically inactive, most of them, unless they have point defects or other things that segregate to them, which also can happen. So I spent quite some time looking at those. And then I moved along to Cambridge in England for my postdoctoral work. And I received a National Science Foundation and a Royal Society Fellowship for my time there. This is called punting on the River Cam. And if you have never tried it, I don't think I was actually brave enough at the time to get, I got into a lot of the boats, the punts, but I didn't actually get up there with the stick. So it's not a oar, it's a stick, and you push it down onto the bottom, and then you have to turn it so that it doesn't get stuck in the mud. And that's apparently how lots of people fall into the river, and I didn't want to fall into the river and look like a fool, so I never put myself out there and tried it. But next time I go to visit, I will probably give it a go. So I was fortunate.
I'm
Yes.
sorry to interrupt. It's a little bit hard to see some of your images. They're taking a while to load. Do you want to maybe try turning your video off to see, because now we can see
Sure.
the images. I'm sorry to interrupt you.
No worries, not at all. Let's see.
That's a lot.
Okay, how's that?
Yeah, it's a lot clearer now. Maybe try the next slide.
Okay.
And we'll make sure it looks good right away. Thank you.
Okay, perfect. Yeah, thank you. So I worked at the Cavendish Laboratory, which was the original Cavendish laboratory where J.J. Thomson worked, and all of the like major discoveries, initial major discoveries were made, such as the electron and the DNA helix. Apparently, they were hanging out in a pub just around the corner here when they came up with this double helix idea. And this was the material science department at the time was located in this building, and all of the electron microscopes were in there. So you can imagine that it was very old. It was not like these high-tech laboratories that we have today for our electron microscopes, but we still were able to get, and back at that time, this was around 2004, we didn't quite have the resolution that we have today. So it worked out. And what I did there was tomography. And tomography is, as you know, in a TEM, it is a projection image. So you can imagine if you have a 3-dimensional nanoparticle, what we're seeing is a projection in the TEM of that nanoparticle. So like a shadow image. So what we'd like to do is to be able to rotate this and take lots of different images and perform a reconstruction so we can actually see the three-dimensionality of the nanoparticle that we're looking at. So I'm going to skip over these. And electron tomography, you have a small holder a tip that is smaller than usual. It's 4 millimeters rather than, just a millimeter over our 3 millimeter grids. And you tilt it to many different angles. And then, of course, there are some artifacts if you don't tilt high enough, which I don't have time to go into how you can overcome those. But I will tell you one of the projects that we worked on, and this, again, back in 2004, this was a much more novel technique. And we were able to look at these quantum dots that were forming within the silicon and not staying within the tin layers. And we were trying to investigate why this was. So this was before annealing, and this was after annealing. And you can see that the quantum dots have started forming, but they're not only inside the layers, but also outside of the layers. So we performed electron tomography, and I hope you can see that this movie playing now that my camera's off. And we were able to get, okay, perfect. So we were able to get a 3-dimensional reconstruction, and you can see that the quantum dots are all in these 2 layers. And the white is the silicon. And if we take away the silicon and just look at the tin quantum dots and we zoom up, I call this my Star Wars movie, you can see that there's this one little quantum dot that has formed outside of the layer. So we caught one of those that we had seen in cross-section in 2 dimensions. And then we did higher resolution reconstructions in this area to try to figure out what was going on. If you can notice in this movie, some of them are more symmetric, and some of them are not. And this is because some of them stay as alpha tin, which is the semiconducting component that we would like them to be, and some of them have morphed into beta tin, which is what we do not want them to be. But again, the question is, why is this nanoparticle forming outside of these layers? And how do we get that? How do we get to stop it? So we did some analysis on the particles. So this is a particle, a quantum dot that's inside the layer. And you can see that it fits the shape that it should be in the 001 and 110 projection. And here's a movie of the quantum dot itself. This one is about 7 nanometers in diameter, and it looks symmetric. Now, if we look at that out of layer quantum dot and do the same thing, it's subtle, but you can see that there is some of the quantum dot that's not quite symmetrical here, missing. And if we look at it in the 110 projection, it's missing there. And this is the flip side of it, 180 degrees. This is only 3.5 nanometers in diameter. And what we're seeing is that it's filling a void from one side to the other. There's a longer story to this, but basically what was happening is that there are voids in silicon that are exactly the same shape as these quantum dots form. So the tin was diffusing out of those layers and into those voids, and it was filling by Stransky-Krestanoff, which means it was doing one monolayer coating and then growing 3-dimensionally from one side to the other. So that was the new science that we were able to do based on technique development. And here is that beta tin quantum dot, which was in a different shape than the others. So then I'm going to move along. I came back to the United States and I went to Sandia National Laboratories, but this one was the one in Livermore, California. It's on the same campus as Lawrence Livermore National Laboratory, so it was quite a large complex. They're both NNSA labs, which is National Nuclear Science Security, not Science, Security Administration. So they are Sandia, Los Alamos, and Lawrence Livermore are 3 of our weapons labs, is what we call them. So there was quite high security there. And pretty much everybody who worked there was required to have clearance, even if you were not exposed to it, just because you could be exposed to it. And I had the Truman Fellowship there, which was established by President Harry Truman to attract the best nationally recognized new scientists and engineers. It's a 3-year fellowship. All of the laboratories have such a fellowship now, so you can apply to these fellowships at Argonne. I believe Fermilab has one as well. And it's the motto at Sandia is an exceptional service in the national interest, which really was the start of how I got interested in national lab work rather than university work. because I wanted to have some sort of service to the nation. While I was at Sandia, I took I came back to the 2010 half again, and I took this old 2010 and retrofitted it to become a STEM. It did not have STEM capabilities then. And as you can imagine, it was not an easy task because the equipment is quite old. But one of the scientific accomplishments we had there, because we were not connected to, they were actually in different buildings, but we had on the same campus an atom probe and a TEM, which you guys also have at Northwestern. So you're very fortunate and can do these kinds of things. So I'm not going to tell you how an atom probe works because you probably all know better than me. And we used this holder that has this removable tip that can fit into a fib so that you can make your sample and put it on there. And then it fits into this holder so you can do your electron tomography. And then this little stub comes out and also fits into the atom probe so you can do your atom probe microscopy. And so here is what the tip looked like. And this was silver particles in an aluminum matrix. And I put this dotted line to show you where that aluminum matrix would be. These particles are just the silver particles that you see here. And this is an electron tomogram. So let's see if this movie works. Okay, so this is what the silver particles look like. We can't see the aluminum, obviously, it's just a light background, but you can see that these particles look elongated. Then we took that and put it into the atom probe, and we were able to see, since the Z direction is the highest resolution direction in atom probe, we were able to see those 1.4 angstrom crystalline spacing of the aluminum. And what we did was put these two on top of each other. We superimposed all of the particles so that we could figure out what the artifacts were in both of the techniques. So we can see an evaporation artifact because these two particles should be in here, but they're not. So this is when you start and end to, atom probe tomography data, you can often get artifacts in the evaporation. And if I play this movie, oh no, it's not going to play. Okay, let's see. Okay, so in this movie, you can see that the artifact from the electron tomography is the missing wedge. So that makes the particle 6 nanometers more elongated than it should be. So the combination of these two techniques is really, really powerful because they have artifacts in exactly perpendicular directions. They're orthogonal to each other, so you can get accurate information if you're lucky enough to be able to get it to survive in both an electron tomography and an atom probe tomography. So it takes some work, but I think the atom probe field has also been moving in the direction of doing at least some TEM, because that really helps with the artifacts in the atom probe tomography. And then while I was at Sandia, we started looking at hydrogen storage, and we were looking at these porous palladium particles. And we looked at what we wanted to understand is their stability and how well they could store the hydrogen. And when hydrogen went into these particles, it would expand the lattice. And we wanted to be able to store the hydrogen without these pores breaking down and still, fairly close to the surface. So we want a high surface area. We want the pores highly porous so that there's a lot of space for them to go into, but we want them to be stable. So we studied them with different temperatures. We would heat it up and then cool it down to lock in the pore structure and then do tomography. And similarly, we would increase it until we would see that the pores would start breaking down. Now, this is a tomogram of the inverse. So what you're seeing here is actually the empty space. And so what we're seeing is the pore structure. So we took away the palladium and you're looking at the pore structure. Other than the slight elongation that you will see if you're used to looking at tomography data, you can see that the pores are pretty uniform and they're about 3 nanometers in diameter. When we looked at the pore structure, again, this is the inverse. What you're seeing in blue is only the pore structure, and ignore these surface effects from the reconstruction. But if you look inside, you can see that it doesn't look quite so uniform anymore. There are areas that look like bigger blobs and areas that look like thinner connections. And finally, if you look at 600 degrees, the connections are very few and far in between. Many of them have become these larger bubbles or these separate chains. So what we figured out was that as you start heating them, the pores do collapse and they become bubbles like you just saw in the tomogram. So these are slices through the reconstruction. And this is a very good indication of what's happening. So as you start heating them up, it becomes unstable for them to be pores in this area the palladium wants to fill in. So it becomes thinner and thinner in the pore region and gets bigger at the intersection regions until it snaps and just becomes a bubble. So this work allowed us to understand that we had to form the particles in a different way. We had to synthesize the pores in a different way in order to keep them stable. So then what we did, I moved on to UC Davis as a professor. And at this time, I went to the Chemical Engineering and Materials Science Department, whereas I had done my PhD in physics at UC Davis. And with these talented students that I had there, we started to do in situ liquid imaging back in 2009, right around the time when this was first introduced. We were making our own chips and trying different things. And basically, you all know it's pretty common today to do in situ microscopy. You will put a drop of whatever your liquid is in between two the green part is silicon nitride windows, which is this part right here. And of course, it's supported by a silicon support and silicon chip. And what we wanted to do was continue on with this work that I had started at Sandia, which is the palladium pores. We want to understand how they synthesize so that we can understand how to synthesize them better. So we wanted to grow them. We wanted to synthesize them in situ. So we're looking at a palladium salt solution and the surfactant, which is what creates the pores. So this is both in STEM. It's a dark field, bright field pair. And what you can see as we turn on the beam and take this movie, this is sped up by 8 times. It's an 80-second real-time movie. You can see that the palladium particles are growing in the solution. And they are moving around. You'll see this movement as the particles grow and clump together. So we're like, okay, this is what it looks like when you're just looking at the palladium salt solution. Now, if we look at the surfactant with the electron beam induced growth, I don't know what happened there. Okay, here we go. You'll see that the bright areas again are the palladium, and they are reaching out towards each other to form pores around the surfactant. We can't see the surfactant, but we know that they're there because they're reaching out and forming these like wires around the pores to try to reach one another. So we formed a porous thin film, which is not what we want because we wanted to emulate the particle growth. So what we did was a partial chemical reduction to get it started in the right direction, and then we put it into the TEM. And now we start seeing what we really wanted to see, which is how do these porous nanoparticles form? We have 2.5 nanometer particles come together and form into 5 nanometer particles. These are the initial stages of growth. Then at later stages of growth, we have these smaller particles come together. And you can see that they are kind of porous clusters. And these smaller porous clusters come together to form the nanoparticles. And this is why the nanoparticles are polycrystalline, because they have lots of different little clusters coming together to form one nanoparticle. So here are some of those porous nanoparticles that we formed in situ inside of the microscope at the end of this movie, basically, as a result of this growth. That is what we see. And this is very similar to the particles that we looked at that were grown ex situ in the laboratory using tomography. So we know what the method is now based on this surfactant of how to grow these particles. And we did work to change that so that we could have aligned pores, so that the pores wouldn't interact with one another and then would become more stable. As a result of this work and my time at UC Davis, I was honored with the Presidential Early Career Award, and here I am standing next to President Obama. This was in 2010. This is me here. I was a little bit shy, and I didn't want to like push my way up because they said, "Okay, who wants to stand next to the president?" And I don't know. We were told to kind of like stay away from him, and then he put his arm around people, but we were told not to touch him. So it was all very strange. And but we got through it. It was really amazing to meet him and to shake his hand. And then the next day, I got to go to the Department of Energy's headquarters and be presented by Stephen Chu, who was the Secretary of Energy at the time, with the DOE's plaque as well. But what I wanted to show you is this award. If you zoom up to it, it says what it's for is innovative research at the frontiers of science and technology, and for exceptional potential to shape the future through intellectual and inspired leadership. And my time in DC for and being with all of these, I think there were 75 or 80 other PCASE award winners at that ceremony, is that I was really impressed by the depth. We sat in this auditorium and we looked out at the stage that had leaders from all of the different agencies. And I thought, wow, it was my first time being exposed to how the government does and affects science. And I thought, I want to have a career in this. I want to do something like this. So I was already a professor at this stage. I mean, you can see that it's far in my career. I mean, if we're looking at like graduate school or postdoctoral, because people always say, you're in graduate school, what do you want to do when you graduate? Do you want to be a professor? Do you want to do this? Do you want to do that? And I would say, it's hard to know those things because you have to have time. You have to have time to go through things and see what resonates with you and see what doesn't. And so this resonated with me. And I decided that I did not want to be a faculty member anymore. So I moved to another national laboratory, National Lab number 3. And this was Pacific Northwest National Lab in Richland, Washington, which is quite the middle of nowhere if you've been there. But there is a river in the middle of this desert. And so, the river is where everybody goes to hang out. And of course, the campus is all nice and green, and the rest of it is a desert, which, this is quite a strong contrast here. But PNNL is the location. Also, Hanford is not far from here. So they were doing a lot of the nuclear waste cleanup there. So it has a lot of history and a lot of history on that site for sure. So I continued my work with liquid stage imaging there. And what we started there was heating in situ. That's when right around that time, heating in liquid holders was released. And I had been doing catalysis since I was a faculty member, but the group that I moved into at PNNL was a catalysis group. So we got a lot more into looking at zeolites, things formed in solutions, and trying to understand zeolite synthesis, which is quite a difficult thing to do. It's a multi-billion-dollar industry, and we still don't understand it, but we're still working on it. So we put in this gel. So we put in a zeolite gel because we wanted to figure out how this was formed. And we found these existing amorphous particles. And then we wanted to look at what is the effect of the electron beam first, because that's always the first question I get. And I'll show you that the particles at 1690 electrons per nanometer squared do kind of change their shape. But the particles, if you just click down and reduce the dose, do not change their shape. So you can see that they're moving around, but they are not morphing into a different shape. So then we looked at what happens when you heat it up. And you can see that, I'm going to have to speed this one up too, that there are these particles that are still here, but there are these other particles that are growing from solution. So you'll see some popping up So there's one growing right there out of solution, and more that are growing out of solution and coming together. So the story is not over. And actually, we just received DOE funding while I've been here at Argonne to continue this work, because zeolite synthesis is so important to industry and to many sectors that we're trying to understand this. But the technology has to come along, because if we don't have the technology development, we can't answer the scientific questions. And we couldn't continue to answer any more scientific questions than just that little bit that I showed you, because there was a polymer coating on this chip. And this synthesis occurs with pH around between 12 and 14, and at elevated temperatures at 70 degrees. So it just ate right through that polymer coating and then hit the contacts, and then it short circuited. I mean, nothing happened to the microscope, but the experiment stopped. It wasn't heating anymore. So like I said, this is something that we're continuing to work with, looking for different chips, looking for different coatings, looking for different materials so that we can understand this important synthesis. I have been interested in government and have been involved in some things. Like at PNNL, I was involved with former Secretary Perry's visit, and this is Congressman Dan Newhouse, who was in Washington's 4th District. And here I am teaching Secretary Perry how to take a TM image. He actually did quite well. He spent some time focusing, and he took quite a nice image. I'm active with the Materials Research Society, and this is something that for the students and postdocs, I would encourage you to get involved, because it's a volunteer organization, and yearly you can go to Capitol Hill. Well, we haven't been able to go this year. We did it virtually this year, but usually you would go to your state's senators and congresspeople and advocate for science. So this is something also that I'm very passionate about. And here I am with Congressman Foster in two different locations. He's kind of my buddy in Congress now, because he's I think he's still the only I think he's the only PhD physicist. I don't know if he's the only scientist with a PhD in Congress now, but I continue even with him to meet and talk about science. And he's one of our great advocates. Of course, he was at Fermilab for many years. So moving to Argonne, and I'm going to wrap up. I know my time is up. The last thing I'm going to leave you with is ultrafast electron microscopy. We just built an ultrafast electron microscope. It combines a laser table with a microscope. The electrons, there is no mechanism to get them to come down the column at femtosecond timescales. So the only way that we can do this is through using lasers. There are femtosecond timescale lasers, obviously. So we use that. We use a femtosecond laser to come into the column, hit a mirror, and go up to the cathode. We photoexcite the electrons from the cathode, and they come down the column. And at the same time that the electrons hit the sample, well, just before they hit the sample, we photoexcite with a second laser the specimen. So then we have time resolution that is on picosecond to femtosecond timescales. And because it's a TEM, we have nanosecond spatial resolution, and we can do imaging, diffraction, and spectroscopy to understand materials dynamics in non-equilibrium. Here's a picture of our setup, and this is right before we had to put up all of these walls, because it's a user facility, so we had to put the shielding around this laser, this several lasers. It's a 40-watt laser, it's a class 4 laser, and it operates at a lot of different wavelengths so that we have flexibility in our user experiments. But that's what makes it dangerous, because there is UV and infrared laser wavelengths in there too, which you can't see with your eye. So it is completely covered now. So when a user comes in, we would do all of the setting up the laser before they arrive, and then the user could come and sit at the microscope to perform the experiments. So we have Dr. Haihua Liu and Dr. Thomas Gage, who are in charge of running the instrument. This is when we only had like half a column. I think the column hadn't been raised yet, and only just the beginnings of our laser system. And Richard Schaller, who some of you may know, he has a joint appointment at Northwestern. He has been our help with the lasers because he has expertise in laser spectroscopy. So I hope you can hear this. This is our building of the UEM. That was quite patriotic music there at the end. But I'll just finish up by telling you that we can operate the UEM in these two different modes, but we're operating in stroboscopic mode. So we are looking at around 1 to 100 electrons per pulse. We can get sub-nanometer spatial resolution, sub-picosecond time resolution, and sub-eV energy resolution, but not all at the same time because the electrons don't like each other. We do have a direct electron detector, and the processes that we're looking at are reversible. These are the range of spectra, the range of wavelengths that I told you that we can achieve. So we can really tailor this to the user experiment. And this instrument just opened now for this user call. The proposal call closed on March 5th, but it will be open to users. So if you have an idea for work that you'd like to do and processes that you'd like to study on ultrafast timescales, it is a user facility open to users now. So I am going to skip through this because I know that my time is over, but these are just some of our initial results that you can see that this is time resolved. This is on the picosecond, whether it's polarization or this is plasmonics in different shape nanoparticles. Okay, thank you so much for your time and your attention. And I'm going to stop sharing so that I can see you all now.
Thank you so much. That was amazing. We're so happy to have you here. We're happy to take some questions too, if anybody has any questions for Dr. Arslan. So with the UEM, what are the key materials that you're interested in studying? And are there material compatibility issues?
What do you mean by compatibility issue?
Stephanie, do you know who posed this question?
Yeah, so I think the question is like, what are the key types of materials that you're interested in studying with this sort of technology? And are there limitations? Like, is it harder with softer materials or that sort of thing?
Yes, it is definitely harder with softer materials. The main challenge, and in fact, the resolution, even if we can do everything that we can to get the electrons to behave properly and squeeze them together so that we have better time resolution, better spatial resolution, we still can't do anything about what happens at the specimen. We can't control what the specimen does. So that actually ends up limiting our resolution. So plasmonics is one of the big areas that we can look at, especially with a spectrometer. Many of the UEMs around the US don't have a spectrometer, so we're a little bit unique in that way, especially in this area. Although at UAUC there is a spectrometer there now. I don't know how far along their instrument is. But looking at plasmonics of nanoparticles And we're hoping to look at some quantum materials, such as defects and how they interact with one another. If you have like two NV centers that are close together and you excite them, for example, can you see what's happening with their dynamics at the faster timescales? There are so many things that are happening on these picosecond timescales that would be very, very interesting to observe. And we're working with SLAC, which is the MEV, ultrafast electron diffraction center there, to try to look at some of their materials as well. The users that use that facility also are coming to use our facility. So another thing that we look at is phonon dynamics in materials, and we would like to probe them, for example, at interfaces of 2D materials. So quantum materials, like I said, the damage that I was talking about for the materials, it can happen on any material. So it takes time to adjust the laser such that the laser doesn't damage the material, but is able to excite it into a state. And it's not just the wavelength, it's also the repetition rate of the laser and the energy of the laser. So they're quite complicated experiments, but once you get one to work, it's really amazing that you can actually probe these non-equilibrium dynamics and answer some questions that we have never been able to answer before, such as new phases in carbon, for example. That's one of the things that we've recently been trying to look at.
Awesome. It sounds like a really cool technique. So I have another question here. It says, how familiar were you with the science of your projects before you joined, for example, catalysis, and did that inform what opportunities you applied for?
It's really interesting, and it's kind of a funny story, but when I was a graduate student and I was working on gallium nitride and semiconductors, my colleagues in the group were working there. I had one or two other, graduate students who were working on catalysis. And I remember saying, I will never work on catalysis. I hate catalysts. and then just a few years later, I started working on it, and I've been working on it for like at least a decade now. So everything that I thought I wouldn't do, ultrafast microscopy was also another thing that I was like, I'm not going to do that. I'm doing tomography. Tomography is my thing. But I didn't plan. That's kind of one of the other things that I wanted to say, is that I didn't really plan my career trajectory. I think it just kind of happened the way that it did, and I was fortunate in the things that happened. And that's one of the things that I always say to young people when I mentor them now, is that you do have a choice, and there's a lot more female mentors around now than there were at my time. And I am happy to be one of them for anybody here who would like a mentor. Because I think it's really important to get the female perspective. There's a lot of things that we haven't talked about, but maybe we'll talk about in the panel session regarding work-life balance. And, as women, we are the ones having children, right? And we have to figure out, there's just a lot of stressors that come up in life, and how you keep on going and maintain a career. It's very difficult. So I want to be an encouragement to all of you that you can continue, and that you should continue, because the world needs all of you women to be doing the jobs that you're doing, and more. We need more women. So I don't know if I answered the question. I kind of went off on a tangent, but.
A very important tangent, so I appreciate that. We have another question. As a grad student who started electron microscopy recently and also has similar interests related to government works, what is the best way to engage myself to learn and also figure out if that is the path I need to invest in?
Yes, great question. What I would suggest to you that I didn't have the opportunity to do, I didn't have the knowledge, I guess, at the time. I was at LBNL as a graduate student, but nobody told me what it was like what the differences were at a national lab versus a university. So there are lots of programs now. One of them is the DOE Office of Science Graduate Student Research Program. So it's SC for Office of Science, and then Graduate Research Program. I think it's program at the end. So that would be a way that you could apply to do anywhere from, I think it's 3 months to 12 months of your PhD research at a national laboratory. And the person asking the question, I don't know if you are here at in Illinois, but if you are, you can definitely apply to come to Argonne as your national laboratory, or you can go somewhere else if you'd like to visit a national lab. As long as there's a person there who you have that you can make a connection with. You don't have to have a connection with them already, but if you make a connection with them and you then find a research project that they will support you and help support your nomination for this award. We have 2 or 3 of them at the CNM right now. And even with COVID, I believe they are enjoying their time having access to all of the different capabilities that we have. And then importantly, while you're there, you should ask your staff member to talk with you about the ways that all of the differences in national labs versus universities, because there are quite a lot. And postdocs even are not generally, the staff members try to shield the postdocs from this, which I don't agree with. So postdocs are always invited to all of our division meetings, our safety meetings, our group meetings, because I want the postdocs to experience what it's like to be in a national lab so they can figure out if they want to do that in the future or not. Now, barring the DOE award, you can just come to the laboratory as a user at one of the user facilities like the CNM, or you can build collaborations and come and work with a scientist at the national lab with collaborations. So I think the most important thing is to build scientific collaborations with somebody in your area, and I think your PhD supervisor should be able to help you with that.
Thank you. So Dr. Arslan, I want to thank you again for your wonderful talk and for sharing your experiences. This is just awesome.